Hey everyone, welcome back. This video I'm going to be focusing on vapor-liquid equilibrium. So I'm going to go through a lot of stuff in this video. So I'm going to start off just a little refreshment on nomenclature. It's going to be really quick and knowing what the symbols I'm going to be using mean. And then I'm going to talk about the Antoine equation, which is super useful. Then I'm going to show you how to determine if I'm a vapor, if I'm a liquid, which from this point on is going to be really, really important for vapor-liquid equilibrium, and we're doing fugacity for the rest of the course, really important. Then I'm just going to give you a little what is VLE, so we can know what I'm talking about. Then I'm going to get into Raiuls Law. And then modified Raoult's law, and then I'm going to finish off the video with Henry's law. Alright, so to start, just a little refreshment on nomenclature. So when I'm using X subscript I, I'm going to be talking about liquid mole fraction of species I. So liquid mole fraction. Mole fraction of I. So that's defined as X. Here, I'll put this in blue maybe. Xi equal to Ni liquid over N liquid. So for X subscript I, we're only looking at the liquid part of the system. So for example, if I have water and steam in some mixture, well, that would be one component actually. So what am I saying? If I have, I don't know, methane and hexane in some mixture, and I have liquid and vapor in that mixture, then if I'm looking just at methane, I would just be looking at the liquid part of that mixture and how much of the methane is in liquid. So the same thing goes for Y subscript I. I'm talking about, well, this time it's not the same thing, but I'm talking about vapor mole fraction of I. So it's the same idea. Yi is equal to Ni vapor over N vape. Z subscript I is the mole fraction of I in the system. Mole fraction of I in system. So if I have a mixture of hexane and butane, let's say, and I have liquid and vapor in some jar, my Zi is how much hexane do I have in the system. So is it 0.5? Is it 0.1? Which is it 0.2? How much of that species is in the, forgetting about liquid and vapor, just how much of that species is in this system. So your Z subscript I is defined as Z subscript I equal to Ni over N. So Ni being moles of species I, and then divide by total moles of both, or of all the species in the system. V subscript N is how much of the system is in the vapor phase. So like I said, I have a cylinder with vapor and liquid. Well, how much of that cylinder is vapor? How much of that cylinder is liquid? How much of system in vape phase? And it's probably pretty obvious. L subscript then, how much of system is in the liquid phase? How much of system in liquid phase? So if you want to say, if you want to know, if it's more clear for you to see an equation, V subscript N would be moles in vapor over total moles. L subscript N would be N liquid over total amount of moles. And also, I want to clarify, well, not clarify, but just remind you of a few key things. That if I have a mixture of different species, where the heck can I write this? Maybe up here I'll write it. Your sum of your liquid mole fractions is going to be equal to 1. Sum of vapor mole fractions equal to 1. Sum of their mole fraction in the system, of your species in the system, all of them equal to 1. This makes sense. Like 1 being, you can think of it as like 100%. It has to add up to 100. And also that my ln plus vn will be equal to 1. So I'm looking at fractions. So it has to be either liquid or vapor for what we're going to be talking about in this class. So if I have 0.2 of my system, which is all liquid, then I know that 0.8 must be vapor. So 0.2 plus 0.8 will be 1. And then lastly, you're going to see PSAT used a lot for the rest of this course. So what saturation pressure is it's the pressure of a vapor, which is in equilibrium with its liquid. So pressure of vape in equilibrium with its liquid. With its liquid. So yeah, hopefully that makes sense. I can do well, in my video where I'm going to be explaining graphs, I'll probably do a little drawing on just to reiterate what all these symbols mean and what they mean physically. So you'll see that in my example video on VLE when I'm looking at graphs. I'm definitely going to go over these again if it's not that clear from this video. All right, next I want to get into the Antoine equation. So that's the Antoine equation is going to be used a lot. It's so simple, but it's really useful in getting the saturation pressure just from having a temperature. So for example, if I need the saturation pressure for a species, which you're going to see is in like all the equations I'm about to show you, if I have a temperature, then I can get the saturation pressure. So A, B, and C, these are constants. So you're going to see them in the table here. A, B, C. So if I'm looking at acetone, for example, that's the first one up here. I have my constants A, B, and C. Then I just got to plug those into my Antoine equation. And remembering here, actually, the key here is T is in degrees Celsius. And then I'll get ln PSAT, do inverse ln, get my saturation pressure. Really straightforward. Not much to talk about here. All right, phases. So something which is really important is to know if you're not told what phase am I in? And am I in a liquid? Am I in a vapor? And this goes back to when I was talking about fluid equations. So when I was telling you guys like beta and kappa, for this course, that's usually going to be for liquids. So or if I'm using an ideal gas equation, or if I have a real gas, if I have a liquid. So that's going to be more important for maybe fugacity, which is going to be coming up. So from this point forward, it's important to know what phase I'm in. So like in fugacity, you're going to need to know if you have a liquid or a vapor, and that's not necessarily going to be told to you in the problem. So you're going to have to figure it out. So if my saturation pressure, which I said can be calculated from Antoine's equation, or there's going to be other equations I'm going to show you coming up, but if my saturation pressure is less than the pressure of the system, then vapor phase is not possible. So therefore I'm a liquid. And then if my saturation pressure is greater than the pressure of my system, then let's say I have some cylinder with a piston. This piston is going to move up, so we're just not going to be in equilibrium. No equilibrium possible. But if my pressure is equal to my saturation pressure, then I am in equilibrium. The pressure of my system, if that's equal to Psat, then we are in equilibrium. Yeah, I think that should make sense. And if my P external is equal to Psat, then I'm going to be having a phase change. Yeah, that's basically it. Number 1 is the most important though. So if my Psat is less than P, then vapor phase is not possible. I am a liquid. All right, so I don't know what I was writing here. What does VLE mean? What does vapor liquid equilibrium even mean? It's when the rate of evaporation is equal to the rate of condensation. So let me write that. When rate of evaporation is equal to the rate of condensation. So up until this point, there's a few other criteria which I'm going to add to this list when I'm talking about fugacity and things like that. The criteria in order to be in VLE are as follows. So T alpha equals T beta, P alpha equals P beta. Where alpha and beta, these are phases. So the temperature of the liquid phase is equal to the temperature of the vapor phase. So this is a phase. Alpha is a phase. Just some general symbol that I'm using. Yeah, then I also want to talk about really quickly is you guys have seen phase diagrams before, and you know that phase diagrams are super, super important. You're going to be seeing them a lot, especially you're going to be tested on it, and they're really useful. So really quickly here on the side, I'm going to show you the two kinds of phase diagrams you might encounter. So here I'm going to be talking about multiple species. So this is typically you're going to see binary mixture. So maybe I'll write here binary mixtures. So I'm talking about vapor-liquid equilibrium between binary mixtures. So toluene and methane in a jar. What does this graph look like? So here I'm going to draw on my axes. So if I have a pressure versus, I won't do that in blue. How about I do that? Maybe something like this orange. So pressure, and then I have mole fraction. And we know mole fraction can only go up to 1. So mole fraction. So this mole fraction might be mole fraction of liquid, mole fraction of vapor. It's just mole fraction for now because it's going to depend where I'm looking on the graph for what that mole fraction is. So just mole fraction in general. And this is going to be 1 because we know it only goes up to 1, my graph. So for example, if I have 2 species, I might have something like this, and then my other species might look something like this. Or I might have something like Again, just say black is one species, green is my other species, something like this, okay? So my first graph is a pressure versus mole fraction graph. So if I'm talking about phases, because I said phase diagrams are really important, where would my liquid and vapor be on my graph? So that is the key to what I'm trying to introduce you to in a phase diagram. So here is my liquid, here is my vapor. For my other graph, where I have a temperature versus mole fraction graph, it's the opposite. So here is my vapor, and here's my liquid. Not too difficult. Yeah, just look for, you can maybe, if, yeah, no, that's basically it. Yeah, so everything you see here, this here, what I just colored in red, in here, that's when you're in equilibrium. That is when you are in vapor-liquid equilibrium. You're in equilibrium with your vapor. So I'm going to get rid of those. I don't really think those look too nice. Some more kind of definitions, or whatever you want to call it. If I'm looking at my pressure versus mole fraction graph, you guys have probably heard of saturated vapor or saturated liquid lines. So my saturated vapor line is my green line. So saturated vapor line. And my saturated liquid is right here. Saturated liquid. And then you've also probably heard of bubble point or dew point. So you know that your bubble point is your first drop of vapor. So what color can I use here? If I'm looking at this specific pressure, well, for that pressure, here's my bubble point. Bub, all right, bub. Because it's my first, if I'm going along this line, I'm coming in here. Here I'm all vapor. What am I doing? Forget what I'm saying. This here is not my bubble point. This is my dew point. I'm sorry. So I'm going to write dew. So if I'm going like this and I'm making my way here, I'm all vapor. My whole system is vapor. So I have two species and they are both completely in the vapor phase. And I'm going to make my way here. We know this is my saturated vapor line. So as soon as I hit my saturated vapor line, that means I get the first drop of vapor, my first bubble. And then this line here, well, it's just the opposite. This is my bubble point. So if I'm looking from the y-axis and I'm moving my way right along this line here, I am all liquid. And then as soon as I hit the saturated liquid line, I get my first bubble. I start to boil. That's what I'm saying. And then the same thing is true for my T versus mole fraction graph. Pretty straightforward. Again, this is going to be reiterated really, really in detail when I do my example video on how to read VLE these graphs. All right, next I want to get into Raoult's Law. So here it is, up here. This is the famous Raoult's Law. So it's the pressure of my system times the vapor mole fraction of some species, which is equal to the liquid mole fraction of the species times the saturation pressure. Again, just to be clear, this saturation pressure can be obtained from Antoine's equation, which is what I showed you at the beginning of my video. Yeah, and we also know that what I said before, actually, no, I don't want to say anything more about that. Also, here, when I'm talking about binary mixtures, which is the key to this class, so if I have like hexane and toluene in a jar together, let's say, and I say, oh, okay, what is the bubble pressure of this system, this equation is going to tell you that. So this is going to tell you bubble pressure. So if I say, what is the bubble pressure? Okay, then you're running to this equation. If it's better to understand where the equations come from the proofs you're going to see in class, but if you don't have time and you're just like, what equation am I using? Bubble pressure, this is the equation I use. And I just said bubble pressure, bubble point is when you get your first drop of your first bubble from your liquid phase. So if you want to think of it going from the liquid phase and getting the first bubble, then remember this little x, which is the liquid mole fraction. I'm going from the liquid and I'm getting a first bubble. So I'm mostly liquid at this point. It's only one little bubble. And then here, same thing. This here is used for dew pressure. So if you need to remember, think of it as dew pressure as being the point where I get my first drop of liquid. So I'm starting from the vapor and I'm getting my first drop of liquid. So since there's going to be more vapor at my dew points, because you're only going to have a drop of liquid, that's why I have the y. That's not why, but you can think of it that I'm going to look for my vapor mole fraction. Yeah, in my equation. So yeah, that's Raoult's law, and when you're going to use Raoult's law is really, really also important. So when I'm using Raoult's law is when you have evidence or it's said that the vapor is an ideal gas, or, well, also not or, it's also liquid is an ideal solution. So it's either going to be said, oh, the liquid is an ideal solution, or you might be given, something might be written like, the species in my container are chemically similar. Species are chemically similar. So their formulas are similar to each other. Yeah, so if it says something and you're reading your word problem and it says species are chemically similar, then that might be good enough proof for you to write as an assumption, oh, the liquid is an ideal solution, and you have some evidence where it says that vapor is an ideal gas. Okay, then I can use Raoult's law. It applies to what this is saying. The next one is modified Raoult's law. So here, you're going to notice we have a little gamma, so you're going to need a correlation for it. So you really, you can't use modified Raoult's law unless you have a correlation for gamma, or if you have everything known and you're looking for what gamma is. So again, just underneath, I'm talking about multiple species, which is usually going to be a binary mixture, but it can be more for this class. So my first pressure up here is going to be for bubble pressure. Bubble pressure. And my second pressure down here is for dew pressure. So again, think of it as the same way as before. If I'm on a test and it says, oh, what is the bubble pressure with this liquid mole fraction, whatever, blah, 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 this temperature, and you're like, oh, like I don't have time to think, I don't know what I'm doing. Well, just remember, I don't want to say memorize, but just know, okay, bubble pressure, well, I'm got to use modified Raoult's law because I have this gamma here. And I know that bubble pressure is when I get the first drop of a bubble, a first drop of vapor. So my whole system is basically liquid. So I'm going to be looking for this, my liquid mole fraction. And same thing if they ask, oh, we need the dew pressure, well, that's your first drop of liquid. So your whole system is basically in vapor, and you can think of it as, oh, here's my vapor mole fraction. Yeah, just maybe some tricks to remember. All right. So when am I using modified Raoult's law? Well, you need two things. So the vapor is an ideal gas. So you're going to have to look for that being written somewhere in your problem. And you're also going to have to look for liquid is not ideal. So you're going to have to look for these two things in order to be like, okay, modified Raiuls law will apply to this specific problem. All right, Henry's law. Here it's not too complicated. You know that, so here again, here's our mole fraction in the vapor times pressure equal to mole fraction in the liquid times Henry's constant. So you know, first of all, that you're not going to use this unless you have Henry's constant or you have to solve for Henry's constant. So that's the first thing. This will never apply if you don't have anything being said to you about using Henry's constant. So need Henry's constant or you're finding it. So it's going to be really simple for you to be like, okay, I'm using Henry's law, or you're finding it. Which I've never seen a problem where you're finding it. It's usually you need Henry's constant. But who knows? You never know. When am I using this equation? So you're going to have some non-ideal mixture. Non-ideal, but intermolecular interactions are constant when the concentration is low. And usually a Henry's law problem is going to be having to do with a gas being dissolved in the liquid. So that's what you're going to be looking for. Gas dissolved in liquid. That's the key. That is what you're looking for in your word problem. Gas dissolved in liquid, and this H, something telling you about Henry's law. So yeah, Henry's more like modified Raiuls law and Raiuls law. You're kind of figuring out which one am I using. For modified Raiuls law, you're going to be looking for gamma. You're going to have some correlation for it, or you're going to be looking for gamma, and you're going to have to decide, am I using Raoult's or modified? It's a bit more tricky, but Henry's, it's always going to be really, really clear that you are using Henry's law.